Okay, does somebody have the pattern down? You can just tell me. What is the pattern? Threes and fours, right? Yeah, right. That's the pattern. It's a very simple pattern, right? This is why you got to memorize borate. What's the formula for borate? BO3 3 minus. And then the others are easy. But once you memorize borate, then carbonate is? What's the charge on carbonate? Yes, and then what nitrate is? And then fluorate is? Chlorate is? ClO. Yeah, right. Do you see the pattern? This is. Did you miss that particular one? Because we did it like multiple times. This pattern. This pattern is the L pattern here in the periodic table. And this is the next element is boron, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. What do all these have in common? 3 oxygens, good. And so carbonate 3, nitrate 3, fluorate, fluorates 3, chlorate 3, bromate 3, iodate 3. This cuts down the amount of memorization you have to do tremendously because it's a simple pattern. If like I said before, if you can learn the patterns, then you don't have to do as much rote memorization. And the charge, what happened with the charge?
It was from 3 to 1.
Yeah, 3 to 1, good. And so, a lot of people have the pattern memorized. So that's the outer pattern. Then we have the inner pattern. Yeah, the inner pattern has 4 oxygen. Do you have it in your notes or you don't have it in your notes?
I have my notes, I just think I didn't understand.
Okay. Well then, so that's the outer, and then the inner pattern starts with silicate, which is
SO4 too.
yeah, and then I said this is group 3, so 3 silicate's group 4, so it's 4. That's a start. That's a way to remember if you forget, what the charge is. And then all those inner block ones have 4, and then you can figure out the charges based on the
So
pattern.
all inner block ones have 4? So
Yeah. So
phosphate would be PO4.
right. PO4, right. 3 minus. You got to figure out the charges. So there are a lot more than. Like, for example, our book talked about arsenate, right? That's not necessarily on the list in the Chem 4 supplement. So there was more that Wani didn't memorize beyond that. And then you could figure some out that you didn't, that weren't on any list. Germinate, for example. What is germinate?
G-O-4.
Yeah, good. You see, that one is not necessary to make a flashcard for whatever else. Right, and so that's the pattern.
So all the ones under F are just 1 minus?
Yes,
And
all
they're
the ones under F, right, are 1 minus, right.
So then,
That's the outer pattern, and then there's the inner with all 4.
and then you just match the charges over.
Kinda, yeah.
So, and what would oxygen be? Oxygen is just O4 minus?
No, there's no oxate ion.
Okay.
There's no such thing as oxate, so we skip it.
So what about sulfur?
Sulfate is SO4, it's in the inner block, so it's SO4, 2 minus. Yeah. So that's it. Then you had to memorize. Then there were only in addition to borate and silicate, there are a few more that you had to memorize. Chromate, CrO4 2 minus. Dichromate, Cr2. Good.
Oxalate?
You know what? Always. Yeah. Oxalate C2O4 2 minus. Was that it? Acetate. That was it. Acetate was the last one. There are others like cyanate. Cyanate appears on the Chem 4 list, but that one is so rare, you never use it.
What about thiol?
What?
Thiol, cyanate, and thiol.
Thiols, did you already memorize those?
Is it like when you switch oxygen for like
Sulfur, we call it thio. Yeah. So thiosulfate, I didn't ask you to. Thiosulfate is common. So if this is sulfate, then thiosulfate is you change an oxygen for a sulfur. So it gives us 2 sulfurs now and 3 oxygens. Same charge. Plumbic and plumbus. No. You should know those as the old name. And a lot of chemicals are still marked plumbic, plumbus, ferric, ferrous. For the test, I'm not going to ask you the old names. This the lab you had the old names you had to do and the new names. So for the test, it's all right.
for thiol, is it always gonna be a sulfur?
It's always going to be sulfur.
So like if it's like a thiol, cyanate can be S.
Right, cyanate is OCN. This is cyanate, OCN minus,
Yeah.
and thiocyanate is SCN minus.
It's always sulfur? Oh.
Yeah, so when you see thio, we have alcohols. Alcohols are like, this is methanol, CH3OH. This is methane thiol. And rather than calling it a, we call it methane thiol, or it's a thiol rather than alcohol. So thio refers to sulfur. It's not 100%. There are some where they use thio for other things, but usually thio automatically sulfur. It's the sulfur, whatever the oxygen was. And so we have ethers, which are CH3O, CH3, like that. With a thioether, it would just be CH3S, CH3.
What do they call the first one?
This one's called cyanate. This one's on your list you should memorize, but it's not on the list I wrote on the board. The list I wrote on the board, cyanate, how many times are you going to see it? The only time you'll see it is maybe on the test. Cyanate. We don't use cyanate much. And the same thing with thiocyanate. These are so rare that I don't, it's kind of a waste of memory to memorize those. And so these ones you don't have to memorize. And so I didn't bother writing these on the board. The only ones I wrote on the board were oxalate, dichromate, chromate, permanganate, acetate as the 8s that you have to do outright memorization for. Okay, other questions?
Oh, so then from these, if you minus 1 O, then it's an I, and if you minus all O's, then it's an I.
If you minus all O's, the charge gets screwed up. When you minus 1 O, it's an I, the charge stays the same. If you minus all the O's, then it's not the right pattern to use because the charge changes. The charge you get from the periodic table. I know chloride Cl, though. For example, what is nitride?
NO2.
Okay, nitrite with a T is NO2. What is nitride with a D? N3 minus. N3 minus. It's a different charge. Don't get them mixed up. Okay. Other.
No oxygen.
Ide means no oxygen, right? Ide is monatomic, except for some. You know, I wrote the exceptions on the board. Do you remember what the exceptions were for the ides? You know, if you come up with a simple rule like that, then there's always exceptions. And so, usually ide means no oxygen, monatomic. But what about this one? Hydroxide. Does that have oxygen?
Yeah.
And so you memorize the other ides. I called these the polyatomic ides, and I wrote them on the board. You should just memorize those. There's just nothing you can do except to memorize those. You know, there's no trick to learning those ones. And so we had some other ides that were polyatomic that you had to remember. Can you tell me another one? An IDE that I called it a polyatomic IDE.
With oxygen or? Yeah.
It doesn't matter. Oxygen, no oxygen, it doesn't matter. It had more than one atom. What were they? Hydroxide was one of them. What were the others? Polyatomic ides.
Cyanide.
Cyanide was another. That's good. Peroxide's another. Good. So you guys have it then. If not, these get some flashcards or something, or just write them. There are very few I wrote on the board. Very few that you have to memorize. Okay. But of course, you know, it's up to you. Every semester, there are people who don't like to use this pattern for one reason or another, and they just memorize it using flashcards. It's fine. I don't care how you memorize it. You know? Memorize it any way you want. There's a reason for this pattern. The reason for this, you know, after we see a pattern, then what do? We come up with maybe some kind of law, you know, and then we look for a hypothesis. And there's a structural reason this pattern happens, obviously, because this pattern fits very nicely with the periodic table. And we're going to look at the reason this pattern happens when we get to the theory of chemistry. All right, were there any other questions?
For the ides, were there only 5?
The ides,
Yeah.
polyatomic ides.
Like the one we were just talking
All right, hydroxide, cyanide, peroxide. What else? What am I missing?
There's amide.
Amide you don't have to memorize. Amide is the only reason you'd want to know amide is because of its chemical properties. What chemical property of amide stands out? Like really stands out? What chemical property of amide really stands out? This is not one I asked you to memorize. The only reason I brought it up is because you saw it somewhere. Where did you see it?
Homework.
In the homework? Yeah, okay. Where else did you see it?
No.
In the lab, yeah. Where else did you see it? Oh, you saw it on something, on a PowerPoint or on a chart. What chart did you see this on? The acid-base chart. And the reason it stands out is it's because it's one of the strong bases. You know, the other thing, in Chem 1A, I make everybody memorize the strong bases. In Chem 4, I don't. And so it's a good idea. You know, the 7 common strong acids, sure, those are easy, but the bases are a bit more tricky. Because you got hydroxide, you got sulfide, you got amide, methide, etc. Those are strong bases. So you don't have to memorize amide, but amide, you know, we recognize that as being a strong, powerful base. Normally, if you look at the questions, if I give it, did I give amide on the practice test? On the sample test? Sometimes I do. But you know, it's simple because I would tell you, you know, I would tell you what it is, and then I just ask a simple question based on it. Let me see if I did. I've given it, to tell you the truth, I've given it on Chem 4 many times. I don't mind telling you that. And I might give it to this time, who knows? But you know, if you see it here, then you're thinking, oh, it's going to be an acid-base reaction. What kind of what is an acid-base reaction? You inventory, you pick the strongest acid, you pick the strongest base, and react them together. It doesn't matter if it's amide, it doesn't matter if it's hydride, it doesn't matter if it's sulfide, it doesn't matter if it's oxide. You know, we just do the same thing. Or phosphate, carbonate, we just do the same thing we always do. There's only one procedure. There's no special procedure for amide. And so sometimes I'll say sodium amide, I'll give you the name and I'll give you the formula for the ones that I don't expect you to memorize. Okay, other questions? So that was how many, it was that was only 3. Did I write down any more than that? Did I write down more than 3? Okay, hydroxide, peroxide, cyanide, hydroxide, peroxide, cyanide. What else? Does somebody have their notes from that day? Remind me what I wrote. I could only think of 3. There are only 3 that I wrote. Yeah, those are the 3 that I want you to memorize. That's it. Only 3. Okay.
Why is it sulfide on my?
What's that?
Why?
Hmm?
Like what
Oh,
makes
and sulfide doesn't oxidate.
I'm
what
sorry?
makes these like ides different from like sulfide or bromide?
Sulfide, bromide, chloride, iodide are all monatomic. Monatomic anions. These are polyatomic anions. If you see IDE, 90% of them are monatomic. One atom. Yeah. All the monatomic ones you don't have to memorize because you can get it right off the periodic table. You know? So if it's sulfide, you just get it off it's sulfur. How many electrons does sulfur want? 2. Charge is S2 minus. You know, the thing is, don't get tunnel vision. You know, I always am surprised at this. For example, the thing I can't understand is how people can get the charge and the, well, I know why people can get the charge and the formula for dichromate wrong, but it never ceases to surprise me. Why would anybody get the charge and the formula for dichromate wrong? Why? When I give this chart and it's written right here. You know, how could somebody screw up the formula for dichromate and the charge? And then I know why. You know, and this is why I said, at least read this chart once before the test. You know, I know why they missed it, because they never looked at this chart once. They never read through the chart once. They never actually tried to name these once. Otherwise, they would have known. You know, I'm asking for the formula for dichromate. They could have just copied it off the chart. I gave the chart. You know, I say this every semester. But always, you know, and there are always the people absent, but, you know, always somebody screws it up. They'll screw up the formula for fluoride. How can you get the... Some people will write fluoride as F2 minus and silver as Ag2 plus. And it always blows me away when they have this chart here. How can that happen? I don't know. Uh-huh.
Why aren't there 8 oxygens in dichromate?
Because peroxide bonds are extremely unstable. I talked about peroxides very briefly. But if you take 2 chromates and you want to link them together, the problem is if you link them like this, you know, and there's 4 oxygens on each chromate, like this. If you link them together, you'll link an OO. Well, an OO single bond like this, well, what we call a single bond, an OO link like this is very unstable. This is what we call a peroxide type linkage. Peroxide linkages aren't going to hold 2 chromates together. So what we have to do is we have to get rid of one of these oxygens and link it by a chromium oxygen chromium bridge. This is called a bridging oxygen. This happens in biology, you know, with polyphosphates. When you look at polyphosphates like ATP, you know, the triphosphate, they're all missing an oxygen. They're missing an oxygen because you can't do an OO link. You have to do a phosphorus O phosphorus link. In ATP and ADP, adenine diphosphate, where you're taking 2 phosphates and linking them, same thing happens. Triphosphate, you're missing 2 oxygens. Diphosphate, you're missing 1 oxygen. Dichromate, you're going to be missing 1 oxygen. That's because of the link. And so that's an easy way to remember it. However, you might go silicate. How does silicate happen? Well, silicate is actually SiO2, but you know it's tricky, the structure. because of the way we count the oxygens. And so this is the dichromate ion, it's missing an oxygen. And so otherwise you'd expect it to be a Cr2O8. I think I mentioned that briefly when we talked about the dichromate, but I don't remember that so well. A lot of the charges, charges are here. So for example, when I do a copper in a compound, I've always said that this happens, I don't know, maybe a few students, even though I tell you, if you see copper in redox, it's going to go to copper plus 1 or copper plus 2. It goes to copper plus 2. But every semester, somebody will write copper plus 1. They want to be the rebel. This, I don't know. Some people, it's okay, but they're going to lose points. And so, the same thing with the if I give you bicarbonate, how can you get bicarbonate wrong? I just can't believe people can get bicarbonate wrong. Actually, you know why? I shouldn't, normally what I do, though, is I do two-part tests. In Chem 1A, I do a two-part test. In Chem 1A, I do a test without this chart here, and then you have to do the nomenclature. For Chem 4, that's all right. You're still learning. I'm going to make it easy.
The question was, with bi, do you add hydrogen and you lose all charges? Or it's like
No, just each hydrogen, you lose one charge.
you lose one charge?
Because the hydrogen is positive, yeah. You lose one charge. Okay, what else? You guys have questions? So this is, do you remember when we read through this? You're probably thinking, that's a waste of time reading through it, because I spent how many minutes did I spend reading through this? And I think, it pains me to have to read through this. And I think, yeah, it's not a waste of time to read through this, because then you know what's on the list. You should do it too. And so a lot of people might think, it's a waste of time, or it's too long of a list. But it could save you. And so that's, I read through both charts. I think. Maybe I didn't read through that one. You remember this guy? We skipped this guy. This guy you don't have to know the name for. This is a species you'd encounter in Chem 1B. Number 31 on the practice test. Okay, did you see the corrected exam? 31, both of those, or? A?
Yeah.
Has anybody tried? I just posted this yesterday, so I don't know. You want me to do it, everybody, or do you want to try it on your own? We could cover it Wednesday, but anyway, I'll just do this one here. Iron. What's the formula for iron? Is it solid, liquid, or gas?
Solid.
Hydrochloric acid?
HCl.
So this looks like the A plus BX. Did you call that what type of reaction? Single replacement, redox, yeah. The situation is, can we use the single replacement form for this? And so single replacement assigns A should be the what? No, A doesn't have to be a solid, it could be liquid or gas too. A should be the, what are the roles? A, B, X. X is the spectator.
Yeah.
Chloride, is it very reactive?
Yeah.
Is chloride very reactive? No, it's not very reactive. A should be what?
The element?
A should, yeah, it's gotta be the element, but what did I call it? What role did I give it?
Reducer.
The reducer. A is the reducer. Is iron a good reducer? Is iron a good reducer? Metals are good reducers, so the answer is yes. Is iron a better reducer than water?
Yes.
Yes. Yeah. We also have to worry about water. What am I getting at? What I'm getting at is this an exception, or can I use do I have to use the chart method for this, or can I use the single replacement method for this? I could use the single replacement method because there are two ways I could figure this out. One, I could just go through the roles, or two, I can realize that this acid is what type of acid?
Strong acid or okay.
It doesn't matter if it's strong or weak, it'd still work. Even if this were a weak acid, it'd still work. This acid is it's not an oxidizing acid. If it's an oxidizing acid, then we can't use this method. And so this is what we call not a reducing acid. I didn't really talk about reducing acids except for acetic acid, which is a reducing acid. But this is if it's not a mineral acid, right? If it's not oxide, it is a mineral acid, so it should work fine. And then iron is a better reducer than water. And H+, what's H plus's role? That's going to be our oxidizing agent. This is going to be a reducing agent. Then we compare with water. Iron's a better reducer than water. H+ is a better oxidizer than water. So we don't have to worry about water. And so this is not an exception. If it's not an exception, then we're going to form iron chloride. But which iron chloride are we going to form? Iron 2 chloride or iron 3 chloride?
Iron.
Yes, good. Iron 2 chloride. And H. H2. Do the correct formula for that. And then we need to balance this. And then we're going to compare. Actually, we should do the driving force before we compare. So iron versus hydrogen. Which one is more active? Which one's less active? And so let's take a look at the redox chart, which should be here. Iron versus hydrogen. Which one's more active?
Iron.
Iron's more active, and so we're going from more active to less active. More active, less active. Therefore, this is we call a driving force. I want you to show me the driving force, like we say DF for driving force.
The reason that's hydrogen is less active because it's closer to fluorine.
No, we don't go closer to fluorine on that side. We go closer to what's at the bottom, right? Lithium.
But iron is below.
Fluorine's on the total opposite side. We can't compare. It's like comparing, these are your apples, fluorine's an orange. You don't say, okay, what's your biggest apple? Oh, my biggest orange is this. You don't do that.
No,
You don't.
iron is closer to lithium than hydrogen, so it's more active.
Yes, right.
So hydrogen is closer to fluorine than iron, so it's less active. Because fluorine's
No, fluorine's on the opposite side. You must be talking about fluoride.
yes, that's what I mean.
Okay, because fluorine, you don't want to compare to fluorine. They're totally different. These are the reducers. Fluorine is a powerful oxidizer. And so this is what I mean by apples and oranges. Okay, what's the most powerful reducer? Oh, the most powerful oxidizer is fluorine. Does that answer no, it's comparing two different things. So we don't ever mix the sides. When we stick on one side and we stay on that side. And fluoride and fluorine are total Dr. Jekyll, Mr. Hyde type species. Fluoride is stable in redox, not stable in metathesis, stable in redox. But fluorine is super. Fluorine? I used to work with fluorine quite a lot. Let me just finish this really quick. I used to work with fluorine quite a lot, but I didn't like it because when I started fluorine, I was taught the secret handshake. Do you want to know the secret handshake of fluorine chemists?
Yeah.
The secret handshake is like this. The first time you go to the fluorine chemist convention, it's like, hey, how you doing, right? The next year you go there, it's like, hey, how's it going? And then the next year, and then the next year, and the next year, and then you have to retire because you have no more fingers left, basically. So fluorine, and it's true because one time I had a leak in my fluorine system, and you know how I found out I had a leak? I went to go close the valve and my glove caught on fire, like this. And my glove, I was wearing 3 layers of gloves, and I had heavy protective outer gloves. And the heavy protective outer gloves caught on fire. The fluorine, basically, fluorine will catch stainless steel on fire. It's that powerful of an oxidizer. Stainless steel is very hard for oxygen to oxidize. If you heat up stainless steel, of course it will oxidize, start to turn black, right? But fluorine will just immediately start to attack it. I used to store fluorine in a steel box, 1/4 inch thick steel plate box. That way, if there was ever a leak, you close the box and you run away. Basically, it'll take some time to eat through the fluorine. Eat through the box. Okay, sorry, go ahead.
I think what she was trying to say is that because, what was it? Chlorine is closer to lithium, it's a better.
No, chlorine is not close to lithium. Chlorine is on the left side, lithium is on the right side.
No.
You know, to a chemist, you can't say chlorine and lithium. If you mix chlorine and lithium together, you know what you're going to get? Chlorine and lithium will explode. In fact, sodium and chlorine, have you seen the reaction of sodium and chlorine? They want to do 2 different things. This is, you know, the reason I'm emphasizing this so much is because it's extremely dangerous. If you start mixing up chlorine and chloride and fluorine and fluoride, you're in for an explosion. You're going to be one of the early retirees from chemistry because you're going to be missing. You know, it happened in Hawaii, University of Hawaii. Last year, a female researcher there was killed. You know, did you hear about that? Yeah, she wasn't, you know, she was young. She was killed from an explosion, hydrogen. So you gotta be careful. If you mean chloride, be sure, because it's Dr. Jekyll and Mr. Hyde, 2 totally different things. So I'm very much a stickler on that because the chemical properties are so different. Well, let's skip it. I know what you mean, but you know, you got to be careful with what you say. And so let's start it over. Let's start over again. Okay, tell me what you're saying.
So iron is closer to.
Yeah, I'll bring up the chart. What happened to the chart? I got too many tabs open. Okay, here's iron.
Okay, so
Here's iron is closer to what?
it's closer to lithium, so it's going to be a better reducer.
Yes.
But
Good.
it's going to be a worse oxidizer than.
No, iron is not an oxidizer. Iron
Yeah.
doesn't want any electrons.
Yeah. That's,
That's what I mean. Like, you could say iron is closest to lithium, therefore it's more active, or you could go the reverse way and say hydrogen is closer to fluoride, therefore it's less active.
Okay. Yeah, the least active would be fluoride, right?
Right, and because hydrogen is closer to that, it's less active, and because iron is closer to lithium, it's more active.
Hydrogen is, okay, the best is lithium, the worst is fluoride.
yeah.
That's fine. I always do that. I always memorize the extremes. I only ask you to memorize lithium and fluorine because, but I always do the extremes. Lithium is the best reducer. Fluoride is the worst reducer on the chart. The best oxidizer is fluorine. The worst oxidizer is lithium ion. That's fine. You memorize the extremes. Yeah, no problem. That's good. Okay. All right. So yeah, I knew what you're getting at, but be careful because if you start talking about fluorine as being a reducer, then that's big trouble. Because you know about chemical compatibilities, you want to have reducers with reducers. You know, on the shelf, you never put I had an explosion in the Chem 1B lab. And the reason why I had an explosion is because of a makeup lab. A student wanted to make up the lab. So I told that student, okay, if you make up this lab, do not mix your waste with today's waste. Because today we're doing all oxidizers. The week before we were doing reducers. And so I set up 2 waste jugs, one for this student that was making up the lab, the other for the rest of the class. The student put the waste in the wrong waste jug and it exploded. It was a big explosion, but fortunately the cap of the waste jug was open, so it just flashed up like this. The student was a little bit short, so sticking their head inside the hood a little bit, and their face got burnt, their hair got burnt, and it was a big flash, just a big flash of light. But fortunately they were wearing their safety goggles, but the glass didn't break. So that was lucky, very lucky. But you know, it just goes to show, you know, incompatibilities. The thing is, when you make a precipitate, do you worry about an explosion?
No.
No. If you make effervescence, you might worry about an explosion if you seal the top of it. You know, and the biochemists were a crazy bunch because they use dry ice all the time, and so they put these dry ice in these little plastic tubes with a screw cap, and they make dry ice rockets, and so then they have dry ice rocket wars in the hallway back and forth. So they're shooting these little dry ice rockets, but it's just a pressure explosion, and so the worst you can get is a pressure explosion. And so for metathesis and for acid base, when you neutralize, well, I told you when you double A. You guys remember double A? Double A stands for
Acids acids after?
Weak acid.
no double A. This is safety rule in lab. Maybe we need a lab safety quiz. Hmm?
Acids added.
Yes.
Oh.
Yeah. Good. All right. I'm glad. We add acids. Why? Because you could have like steam generated in a little steam explosion. But you know, steam explosion is no big deal. It's not like. But in redox, you get very violent reactions. Why? Because the charges change. When the charges change, in metathesis and in acid base, the charges do not change, and so we don't get this Dr. Jekyll, Mr. Hyde. We just get favorable ion combinations. In redox, the charges change, and so we get huge differences. There's a huge difference in energy between sodium metal and sodium ion. Sodium ion is extremely stable. Sodium metal is extremely unstable. And so redox is very violent, potentially. Even with moderate oxidizer like oxygen and moderate reducer like hydrogen, you know, I was going to do that reaction in lab, but the stockroom got rid of all our hydrogen gas, so we didn't have any more hydrogen gas.
Mm-hmm.
Hopefully it comes in a few weeks so I could do the demo. You could see what a hydrogen explosion looks like. It was enough to kill somebody. But anyway,
Sorry.
what's that?
Nothing.
Last year, you would think, you know, after the Hindenburg, after all these other things, you know, people are extra cautious. All right, so yeah, so we do this, and we got a driving force, and then this is called the CE, and then what do we do?
Balance.
Okay, it's balanced, and then what do we do?
The ionic equation.
Yeah, the ionic equations. I'll write that. What's the ionic equation for that? Iron. Does water break apart the iron? Metal?
No.
If you drop a chunk of iron in water, does water remove electrons or break apart the metal lattice? Or if you drop a chunk of iron in water, does it even react? No. In the ionic equation, we're looking at what happens, you know, what the major species are with water. What about HCl?
It breaks apart.
Into?
2H plus and then 2Cl minus.
FeCl2
FeCl2 also breaks.
into what?
Breaking them into
Fe2 plus and Cl minus.
How many Cl minuses?
2 Cl minuses.
Yeah, one of the most common mistakes people made last semester was they didn't balance these. Like here, they'll put one Fe, one Cl. That's not right. We need 2 Cls for every Fe.
And then plus.
So that was a very common mistake. Another common mistake was people said that iron, when they put it in water, turns into iron 2. It doesn't, you know. Iron just stays as a chunk of iron. Metal, it doesn't go to iron 2. And this is
2H.
2H pluses.
Yeah.
2H pluses. So hydrogen gas changes into 2H pluses.
Just kidding,
It's
it's H2.
just H2. It doesn't change. The ionic and the Ce have to say the same thing. And then we get rid of the spectators, right? Chloride. We already predicted chloride's going to be a spectator over here.
So this is the net ionic equation?
Just ionic equation.
This is the ionic, this is the net ionic.
Oh.
This one doesn't react.
Same procedure that we use for double replacement, we're using for single replacement. If you do the chart method, you aren't going to get 3 equations. If you do the chart method, you just go straight to the net ionic equation. That's it.
Are there ever gonna be more than one spectator?
It depends. Yeah,
Like on the thing, would it be?
I have. It depends on the class, you know. I've given much harder reactions than that. That last semester's class was having a hard time. In the past, there have been classes that have been stronger with these reactions, and I give things like this. I would give like HCl plus KMnO4, potassium permanganate, plus iron. Sometimes I'll go with iron nitrate. So sometimes I'll give that. There are a lot of spectators here.
So what do we do if that happens?
If this happens,
Like, yeah, how do you solve that?
we look for metathesis. What are metathesis?
Single and double replacement?
No. Metathesis would be double replacement, but
So single
I don't call it.
replacement is not with metathesis.
Yeah, single replacement is not metathesis. Single replacement we call. Single replacement falls into what category of reaction? Redox. We could look for redox first. It doesn't matter which one you go for first. I don't care. If you want to do redox first, no problem. Go ahead. But I do it in this order. And this is the way we did in class. We did which one first? Metathesis. And so if I threw in something like this would screw up a lot of people because it doesn't fit their pattern. And so this is why I called it metathesis. Rather than trying to fit a pattern, AB plus CD, I mean, we could try AB plus CD plus EF, you know, and do this. Rather than do that, then we just look, you know, what ions do we have here? H plus, Cl minus. What ions do we have here? K plus, MnO4 minus. And then over here we have Fe2 plus and nitrate. And then we look, are there any favorable ion combinations?
Yeah, so we could do burn first.
We look for precipitate, we look for gas formation, and we look for stronger to weaker acid. There is one that's potentially stronger to weaker acid. That would be this one, H plus and permanganate, which would go to permanganic acid. But there's pretty much no reaction here for metathesis. And then we go on to acid base. Well, this would be double, you know, this would double as acid base. And this would be it. And then we would go on to redox. Now for redox, we can't use single replacement. Do you know why? Because A, it was mentioned earlier, A has to be an element. There are no elements here, these are all compounds. And so it's impossible to use a single replacement method on this one because it doesn't even fit the pattern. And so how do we do this one for redox? We have to use the chart method. And so here, H plus is an oxidizer, chloride's reducer, OA for potassium. Permanganate with H plus is called an oxidizer. Fe2 plus is both an oxidizer and a reducer. Nitrate is an oxidizer when it's combined with H plus. And then we pick the strongest pair and then react them. That's how we do it. We use the chart method. Chart method is just following steps. Like I said earlier, you don't need any chemistry knowledge to use the chart method because everything's given. The chart is given. The only chemistry knowledge you need is how to inventory it. But once you inventory it, you could give this to somebody who's never studied chemistry and just tell them, follow these steps, memorize these steps, and you can do it. And they can do it. Guaranteed they can do it if they just follow the steps. It's not easy, of course, but they don't have to have any specialized chemistry knowledge to do it. Well, let me get this question quick.
That's a good question. Like, what is the difference between CE, IE, and IE?
CE is just an acronym. This just means the complete equation or the whole formula equation, so we don't break anything apart. The IE is the inventory, the major species inventory. So this is called the ionic equation. Here, it's not just ions. Although they call it ionic equation, they want to see what splits apart into ions. In chem, I'm trying to give you a more, rather than when we're talking about lattices, pulling apart, this type of stuff, most people just memorize what they do. For the IE, you split apart soluble salts and strong acids. You split apart soluble salts and strong acids. Soluble salts and strong acids are called strong electrolytes. Electrolytes, they give, like salts in water, are electrolytes because they give ions to a solution. And so these are called strong electrolytes. And we split apart the strong electrolytes. So another way of saying this is we split apart strong electrolytes. There's one strong electrolyte that's missing, one category of it, and that's the strong bases. But bases do not split apart. Bases do something else. I already showed this earlier. Ammonia and water. What forms with ammonia and water? What forms is ammonium and hydroxide. This is called hydrolysis. Bases hydrolyze water. They do not ionize. And so the bases do different. And so I didn't emphasize this because it depends on the semester too, because if you look at my past exams, I just gave you last semester's, but if you look at years past, I've given this, metathesis with ammonia. We just had it in the lab. That was all. But I decided to skip it for right now this semester, and then I'll talk about it later when we get back to acids and bases. Okay, that way I don't do too much at once. So I skipped a bunch of things, including electrolytes. And so wait, but just let me finish this question here. And that is, okay, so we get the inventory. This is the inventory of major species in solution. And then out of that inventory, we look at what reacts. And this is what reacts. So that's a net ionic equation. And that's in your own words. Somebody might say, oh, IE stands for the ionic equation. Well, what does that mean in your own words? Well, that's what it means in my words. All right, what's the question?
So on number 6 on the practice test, I think yesterday you mentioned that was true, but I don't remember why.
Where was it?
So is it chlorate
All right, did somebody remember why? I mentioned Pepcon. Do you remember Pepcon?
Yes.
Pepcon was a perchlorate factory.
Mm-hmm.
What makes perchlorate so dangerous? It just looks like chloride, doesn't it? -1. Chloride's totally stable. People eat it without any pretty much negative consequences. Chloride is in tap water, pretty high levels. Chloride's an electrolyte. People want electrolytes. You know, they spend money to have things like chloride put in their water. You know, because a lot of water purifying systems, like the ones we have on campus here, like over there and in the physics math building, whatever, they first do reverse osmosis, removing all the minerals, and then they add minerals in there. One of the minerals is chloride. They could add back in. So, can somebody answer this one for me? Is it true or false? How many people say true?
True.
How many people say false? How many people can't tell?
Just looking at it, you would think that it has a negative charge, so therefore it must have extra electrons. But
It does have extra electrons. It has one extra electron.
so then it's not electrons.
Isn't
In one sense, it's not. In one sense, remember the happy and unhappy talk?
so isn't perchlorate unhappy, therefore it is electron?
Perchlorate's very unhappy, but not everybody in perchlorate is unhappy. For example, the oxygens are happy because each oxygen, there are 4 of them, and each oxygen is -2, making it very happy. Oxygen loves to be -2, just like chloride loves to be -1. Oxygen doesn't like to be 0, like in air. You know, oxygen is going to try to take electrons from everything. You know, everything becomes oxidized. Your books will eventually become oxidized. The wood, the paper, you know, metals, coins, like this coin here. Actually, I'm still going to use this, thanks. This, but I'll get some. But I'll do this in lab probably, because there's one reaction from the last slide I need to talk about. So oxygen is very happy. Well, that's why we have that extra electron. The extra electron is to make oxygen happy. What's unhappy? Chlorine is terribly unhappy because if that's oxygen, what is chlorine? And so all these charges have to add up. So there's -2, 4, 6, 8. This is -8. And then chlorine, there's only one chlorine. What's its charge got to be? +7, because +7 -8 is going to give us a net charge of -1.
So, but that's not where chlorine wants to be.
No, chlorine wants to be -1. How far away is it from -1 at +7? It's 8 electrons away, because 7 electrons will take it to 0, and then you need 1 extra. It's 8 electrons away from -1.
So then would 6 be true or false? Because you said that
6 is true. It's electron poor. Perchlorate's electron poor. You might not have noticed this. The only people who have noticed this are the people who are paying very close attention to this. I talked about ammonium nitrate yesterday, but somebody's going to say, hey, wait a minute. What did I call ammonium? Did I call ammonium electron rich, or did I call it electron poor? No, I called it electron rich. So some people, I thought I don't want to spend time talking about this, so I skipped it, hoping nobody would notice that, right? I skipped it, hoping that nobody noticed that. But you go to a talk, people are going to notice. People are really focused on what you're doing, because maybe that's their field or something. But this thing, I just wanted to gloss over because I didn't want to really talk about it too much, because I already did over here. But ammonium's not electron poor. Ammonium is electron rich. Why is it electron rich? somebody might think, no, you got it wrong. This is electron poor. It's missing an electron. It's got a positive charge. But no, that's not. It's electron because each hydrogen is making nitrogen,
Oh, nitrogen.
Oh, 4 minus. So
3 minus.
which means that nitrogen is pretty electron rich. But you might think, isn't nitrogen electron happy? Now, the happy and sad stuff you memorize, because having a -2 on something is totally different than having a -2 on something else. So these are things that you memorize because what we need, you know, a lot of people think all that matters is to be able to calculate a number. I could give you the equation for calculating oxidation states. Have you seen the equation for calculating oxidation state? It's not given in the supplement. Well, anyway, here are the rules for calculating oxidation states right here. Actually, this might be better than the rules we have in our book. These are the rules from Wikipedia. But there's another way. Do you remember the other way I calculated oxidation states?
The one that you talked about yesterday?
Well, it's a formula. The formula is based on this. In a compound or ion, the oxidation state sum equals the total charge of the compound or ion. So this is a simple formula. And so we could do that. We could calculate the oxidation state. And we did an example of calculating the oxidation state in acetic acid. Do you remember the oxidation state in acetic acid? What I did with acetic acid, or it might have been methanol or ethanol. Did I do ethanol or acetic acid? I did acetic acid in one class and ethanol in the other class. I can't remember which one.
Which one is ethanol again?
Did.
I think you did ethanol.
I did ethanol. Ethanol is C2H5OH.
Yeah.
I did ethanol?
Yeah.
All right. We do ethanol like this. Ethanol is going to be C2H6O. The reason I put them all together like this is because it makes it easier to calculate the oxidation state using this equation. This equation is going to be based on step 2. Based on step 2, how many carbons do I have? 2 carbons. Is carbon variable or fixed?
variable.
Variable. How many hydrogens do I have? 6. Is hydrogen variable or fixed?
6.
Hydrogen is going to be fixed at
Oh. Let's have
here.
or
Okay, hydrogen has a fixed charge of +1, but adopts a -1 when bonded as a hydride to metals. And so this is going to be +1. Oxygen should be at -2. And so this is the equation. This has to equal the net charge of 0, which means carbon is what? Yeah, -2. That means carbon, each carbon atom has a charge of -2. Now, -2 on carbon is totally different than a -2 on oxygen, which is totally different than a -2 on anything else. And so we have to memorize the happy, unhappy thing. We got to memorize that, otherwise we can't put any value on the number. And so some people, they got an oxidation state, the oxidation state equals -2. Well, what does that mean? And so this is where you have to have the multi-prong approach. Remember the multi-prong approach? The multi-prong approach is we need both theory and factual knowledge. If you have 0 factual knowledge, you say to somebody, oh, the oxidation state's -2. Then they ask you, what does that mean? Then you can't answer if you don't have any factual knowledge memorized.
Can we talk about variable and fixed, please? What does it mean? I don't quite
fixed charge, meaning is that like, it just has like -1, like?
Well, okay, a variable and fixed usually refers to things like this, like group 1.
Yeah.
What's the charge on group 1? Fixed at +1.
Okay.
Group
so
2,
Plus two.
+2. Everything, aluminum,
Plus three.
+3. About everything else is variable charge. Even chlorine. Chlorine is -1, but we see it as +7.
The oxygen's fixed, or?
No, oxygen is not fixed because we see oxygen. I'll show you what we see oxygen as here. We see oxygen as what in peroxide? In hydrogen peroxide, oxygen cannot be -2. If oxygen is -2, then hydrogen must be +2. Is it possible for hydrogen to lose 2 electrons? No, it's impossible because hydrogen only has 1 electron. You can't lose 2 electrons. And so oxygen here is -1. Each oxygen atom. Now, is oxygen happy in -1 or unhappy? Unhappy. Hydrogen peroxide is unhappy. It's a reactive chemical. Compare it to water. Is water happy or unhappy? Water's happy. What are the charges? +1 for hydrogen, -2 for oxygen. So we have to learn this happy, unhappy stuff, otherwise we can't put any meaning to the numbers.
Can we go over the island in the middle again? The charges of the island? Like-
The charges on the island are variable. We don't know the charges. Some of them you memorize. Oh, are you talking about the fixed charged island? What's a fixed charged island?
Zinc.
Zinc is always,
2,
cadmium is always,
2,
silver is always.
1.
Yeah, that's a fixed charge. Everything else is variable charge. Now, am I going to make you memorize it? I thought, no, I'm trying to keep it easy. Some Chem 4 instructors will make you memorize. Okay, what are the charges on iron? 2 and 3. What's the charge on lead?
2 and 4.
Yeah, well, you already have them memorized. Some instructors will make you memorize that, but I thought, okay, this semester I'm going to take it easy. Not. In Chem 1A, for sure, to have you memorize it. But some instructors don't make you memorize any nomenclature. Well, they're going to be in big trouble when they get to Chem 1A. If they haven't memorized anything and now all of a sudden they're going to have an avalanche of stuff to memorize, they're going to be in big trouble. So we're doing like a little bit at a time, you know, not all at once. And so those variable charges, don't worry about it. It's just variable charge. How do you figure out what variable charge? I gave you little tips, like iron. How did we figure out it's going to be +2 rather than +3?
Based on all the
We looked at the redox chart. You look at the redox chart. How do I know it's going to be copper 2 and not copper 1? Well, that's because it was given in the redox chart. So the variable charge, like the earlier question I got today was the ich aus. Remember somebody asked me about ich aus? Those, like, okay, manganese. What is the charge on manganese? Don't worry about it. I'm not going to make you memorize the charge on manganese, you know. Or stannous. What's the charge on stannous? It's 2. Yeah, you got it right, but you know, stannic is 4.
So we don't need to know ich left?
You don't need to know ich aus. That was asked about 10, I don't know, 30 minutes ago. Somebody asked me about that. Ich aus. We don't need to know ich aus. You should know it in the back of your mind. You should know what it refers to, but I'm not going to make you memorize them, you know. There are a whole bunch. If you look at that lab experiment A that I was absent for, there are a whole bunch of ich auses on that lab, including things that are kind of strange, like arsenic and arsenaus. That's kind of a ridiculous name because most people will think arsenic is just arsenic, yeah. But not arsenic. You know what it is? It's arsenic +3. What is? Yeah, I mean arsenaus is +3, arsenic is +5, which is ridiculous, yeah. And so I thought, I'm not going to make you memorize that kind of stuff. It's too much.
Tomorrow, can we spend some time going over the tests?
Well, you know, for each exam, because I got to cover a certain amount of material, we can go over it for a certain amount of time. But I'm going to what I'm gonna do for chapter 10, I was thinking about this, is I need to cover it quickly. And so I'm going to rush through chapter 10 and just hit the key points there, but I need to complete it, otherwise I'm gonna fall too far behind. And so we can go over the practice test tomorrow, but let me start chapter 10 after our break, and then we'll finish chapter 10 today.
Chapter 10, you're not gonna skip around, right?